Hello everyone, Namaste. I am Ramnath who would like to share with you some information on the glimpses of PVT corners evolution. Since we come across many a times as part of the soft design PVT corners and different types we will come across. So thought of sharing some more information on it. This is though basic. So please feel free to give your comments or suggestions. Thank you. Lifetime of a chip usually depends upon the number of failures and the time it survives. So here if you observe, there are mainly three phases. First one is the early life failure time and the useful life period, and this one is the aging period when actual wear out will happen. These times are log scale so this will be usually in a few days, and this will also be sometimes few months to years, but this is the usual time which will be counted. Here it will be usually what is expected is 10 to 15 years, and the number of failures during this lifetime should be very less. It will be counted and measured in terms of parts per million or parts per billion. So lesser the number, better it is. So here, if you observe, to ensure that the chip works in an expected way for a long duration, so it needs to be qualified through simulations in the different PVT conditions which the chip sees during its operation time. So we will discuss here on the process part of the evolution, how it evolved, the process corners, and we will not be understanding the voltage, temperature and other specific scenarios under which the chip will be analyzed. During VLSI IC fabrication, the variation affects the components made in front end of line and back end of line. Front end of line is the portion of the IC fabrication where individual components such as transistors, capacitors, resistors, these are fabricated. Okay, in the case of back end of line, these components are connected through metallization. Here we will be restricting our analysis to the front end of line creation. So that means like how the PVT corners evolution will happen. Okay, so if you go to the back end of a line, the variation is configured or measured in a different way. Okay, through C-bus, C-bus, RC-bus, RC-bus, like that, in a different way. I will come to that at a later point, but in this situation we will discuss mainly the PVT corners, how it evolves. To understand that, we need to understand the components of it, then like what it takes. So if you observe, the wafers are made in a lot. This is one lot. Okay, there will be several lots when the chip is sent to different customers, because the dice, how many comes out of a wafer, and usually 25 wafers will be there in a lot. So but the sales of the chip will be in usually in millions to few thousands in some cases. So we need to figure out how all these things will pan out, and the PVT corners will affect the function of the chip. So if you take one of the wafer, so the number of dice will be somewhat in this way. Okay, so here each one is a die. Okay, So these things are not have to be thrown out. Okay, so if you take this good one, so this will be packaged and you are seeing the packaged IC. So now if you see each SOC will have the process monitors such as these ring oscillators. So based on these ring oscillators, I have shown you the most primitive one. Okay, so this is constructed using the simple inverter, and yeah, we can also convert through NAND gate and NOR gate, even some other gates also. Here I have shown you with the simple gate, and usually these will be in 41, 39 or 541, 539, like that. It depends upon what you wanted to measure. Okay, and the number will be usually odd. Since we have connected this to the beginning one, the output will be oscillating. That is why it is called a ring, and since it makes continuous oscillations, it is called a ring oscillator. So the delay what is obtained at the end of this ring oscillator will be calibrated, and for the several dies in these wafers are sampled, and then you will figure out this to estimate the PVT process corners. Okay, so the delay what is obtained per die and within several dies of the wafer, within several wafers of a lot, out of several lots, all those things are taken to arrive at the mean population standard deviation. Okay, however, we will not be able to compute and calibrate for all the wafers, all the lots of the entire chip production cycle, whole production cycle related data. So we will only sample a few of them. Based on that only we will analyze the data. Before we go into the sampled data from different ring oscillators, I'll just give a brief information on the IC fabrication. Here, IC fabrication is a stochastic process where a random variation and systematic variation exists. Systematic variation is mainly due to the tools and the experts involved. So that can be corrected to a certain extent, but however, the random variation will be very difficult to control. So even though there are so many upgrades happening, still I am saying that random variations are still in the process of evolution. Because of these different processes like doping, etching, chemical, mechanical polishing, all these things, the randomness will come into play. Hence, the sampled delay which we have obtained through a ring oscillator, which is a process monitor, so that will differ from die to die and within wafer to wafer. Hence, when we collect different sample data, you will see that the cell delay is varying here if you observe. Okay, for explanatory purpose, I have considered the 50 samples. Okay, so if you take their mean, it will be so and so time units, and the standard deviation is so and so 26 in this case. And if you take the distribution, Here I have considered the Gaussian distribution. Okay, so it need not be a Gaussian distribution. Please note, it need not be a normal distribution. Sometimes the distribution of the data will be non-skewed versions. Hence, it will not be following the Gaussian distribution. For understanding, we will consider the Gaussian distribution. So based on these data, Gaussian distribution data is figured out, and the data is plotted here. So if you observe these values, 382 belongs to the 3D, the 3 sigma below, and the 3 sigma above value is 538 here. Okay, and this is mean is 460 here. Okay, that is same as this one. And if you observe, the 1 sigma value is this far away, 2 sigma, that means like this point is 2 times the sigma away from the mean. This point is 3 times the sigma away. Similarly, in the higher front, that means like this point is 1 sigma away, this point is 2 sigma away, this one, and each point represents the probability distribution. That means like what is the possibility that this 390 picosecond can occur in different samples. Here also this much, like that the probability distribution will be there, and the total should become 1. So to figure out these things, to give some more explanation, this is the mean value here, and this one is the 3 sigma standard deviation below this point. Okay, and this point is 3 standard deviation above the mean here. Okay, and these are the minimum and maximum values. Okay, if you see this minimum value, this is here. Okay, this point, that is 1.96 in the negative side here in this direction. It is for calculation purpose. This part is considered as negative, this part is considered as positive sigma, and this one is the maximum value. So this is how the distribution of the data is configured in the Gaussian distribution. Okay, again I am telling the distribution need not be Gaussian. Okay, for understanding the evolution of the process corners, we will again consider the distribution of the cell delay, and then we will understand that this mean, whatever we are seeing here, which is having the largest probability distribution. So this one we considered that it is due to nominal or typical NMOS, and then when it has the typical PMOS situation, we will consider that this delay has occurred, and this is their probability. Okay, so this is the probability. That is how we denote this mean, and this first letter belongs to the NMOS, the next letter belongs to the PMOS. So typical, typical, and when we see the 3 sigma value maximum, the cell delay is less here, nominal here, largest here. So here it is due to the slowest NMOS, slowest PMOS. Because of that, this value took place, and this is its probability. Coming to this one, here it is NMOS is fast, PMOS is also fast, hence the delay is very fast. So this is how the distribution has occurred. Now coming to apply it to the actual silicon register to register scenario, we will know that to figure out this and understand it properly, we need to ensure that in setup condition and hold condition, this register to register timing path should meet. Then only we will have less failures in silicon, and hence the lifetime of the chip will be longer. So to ensure that one, in the simulations we need to ensure that this will resemble to the silicon scenario. So assume that we are considering the setup condition. In the setup condition, slow condition, so I'm not talking about voltage and temperature, I'm considering only the process related variations. Here when we are considering only the process related variations, you will observe that since the devices in this one, when we are considering the slow condition, no device will be slower than this part. Okay, so that means like these conditions won't exist. Okay, so we need to consider this one or these items. Okay, so the devices can be slower than this. These items are, these cell delay values are slower than this large value. So to analyze the setup condition further, we will consider that this scenario, this setup timing. Here this is the D coming and then changing into low. Here this is the clock situation. So currently it is having a setup of this much. Okay, so now to ensure that, so D is here. Okay, that means like the clock is coming here in this way and the data is coming through this manner. Okay, now how do we get the pessimistic scenario is like here already this logic is in SS condition. So the largest delay these cells are considering, accumulating. So to this is the only situation we have where we can do some control, and we know that there will be local variations. So these gates can have different delays other than these ones. Okay, which we are considering this as to be in slow condition. So if we make these delays smaller than these ones, that means like these in this one, which is possible. So in this case we are thinking that these devices have slower delay, faster delay than the largest one. That is what we are considering. So when that happens, the data comes early. So now we are creating a pessimistic scenario. With this one, we can ensure that means like with this much derate. Okay, this value differs from technology to technology and different scenario. Okay, nominal condition changes or the temperature changes, these things also will change. Currently we are not talking about VT variation and other variations. So here if we consider, assume that 8% we have considered, because of this the data which comes here will be coming earlier than this, because these items have smaller delay. Okay, smaller delay, so it is coming early. So because of, so that is how we are visualizing during simulations a scenario which mimics the local variations in the dice. Coming to the hold time scenario, so if you observe that a device cannot be faster than the same device at best case corner. Means like there cannot be devices in this fashion. Okay, this is the fastest device we have figured out based on the distribution. So now there cannot be these devices. Okay, that's what it means. So now there can be devices which are slightly more delay than this one. That is possible. These will consume more delay. Okay, this will consume more delay. So this is possible. So to mimic that scenario, this local variation scenario during simulations, what we will do is we will take some derate factor 10% here. Okay, and now we will apply it to the clock path, because now we are thinking that this is coming at the fast corner here. NMOS and PMOS both are in fast condition. So these ones, and this is the whole time condition. And during this time, what we are saying is like these are coming slower. So compared to this one, these items are slower. So these are slower. So we are slowing the clock path by this much amount. So whatever delay, assume it is 0.8 nanoseconds. So then this one we will be increasing it. So 0.8 into 1.1, considering the 10%. So that will be this. So the cumulative data, when it arrives here, this flip-flop sees the clock is coming slightly late. So this is how now mimicking the scenario of variations. Now if you observe, this is the asymmetric derate. That means like derate, whatever 10% or here 8% value, these ones are applied to one portion of the timing path. That means like either to the launch path or to the capture path. This is not the idealistic scenario, because there can be different timing path scenarios wherein this asymmetric derating may not be representing the real scenario in the silicon. So applying derates only to one of the launch or capture paths is not the best way. So what we do is we will move out of asymmetric derating. Asymmetric derating will work properly with the performance corners or FF corners or SS corners. However, they will lead to slightly higher area or higher power consumption. So we will use the global corners. So during these global corners, we can have symmetrical derating. That means like we can, if we consider this one, the devices can be faster than this item in one situation, and some paths can experience delays which are slower than this one. So we can, if we take this as reference, there can be devices in the design which are faster than this. There can be some devices which are slower than this. So that is why we have taken the slightly in interior value towards the nominal from the first corner, and then we are considering this as the global corner near the fast corner. Similarly, we can consider that the SSG corner, which is in between the SS corner and TT corner, and that based on that we can find that some are slower than this SSG corner and some are faster than this SSG corner. We will see further. In symmetrical derating, we will figure out how the FFG, SSG, which represent the local variation at fast corner, SSG, which represents the local variation at the slow corner, will help in easing out the SE analysis and will help in reducing the area and the power of the soft design. So here again we will consider the setup timing. In the setup timing, here SSG is this one, and with respect to this one, the derates which represents the local variation for the early, and this is for the late. Okay, so that means like these devices which fall in this one, these devices may come late with respect to SSG. These devices here, these devices which have probability distribution of so and so will be coming early, because these delays are lesser than SSG. These delays are larger than SSG. Hence, these are called late arrival. These are called early arrivals. So we will figure out how, because of the introduction of the SSG, how we can this STA process will be more helpful. So because now SSG derates are applied, both exist for early and late. Now you will observe that this situation wherein we have earlier during asymmetric derating, we have mentioned that slower than same device at worst case corner, there can't be any device, and also we mentioned that there can't be any device which is faster than the same device at the best case corner. So we can figure out now that in the SSG or FFG condition, these statements won't be valid, so we will remove them. So now if you consider this one, due to this situation, some devices becoming early compared to SSG, data, because we will be applying the early things to the launch path, so data will come early. Okay, and now when you look at this one, these things are coming late. So now if you, so this was present even in the asymmetrical derating, but with the symmetrical derating we have this also. So now clock is coming slightly late because these devices are larger in delay compared to SSG. So these ones. So now the clock is also pushed out. So now the derates are applied both to the clock and to the launch clock path, capture path and to launch path. Same derates or different derates based on the situation. So they are applied, and hence now you will see that all the devices will undergo through variation, and you will see a more realistic representation of the silicon, and hence we will see that this has more chance of surviving during silicon, and also this will lead to lesser amount of area and power dissipation, because now there is no overestimation compared to asymmetric derating. Now we will go to the hold timing. In the hold timing, this timing path, now we are applying the FFG at the FFG corner. Actually, hold timing need to be analyzed in all corners, FFG, TT and SSG, all corners. Okay, any other corners as well. So here in the FFG corner, if you observe, you will find that there are some devices which are slower than FFG. There are some devices which are faster than FFG. So now we will apply that in the early paths to the clock. So the data clock is coming slightly earlier, and we will see here we are applying the late derate. These are the late derates. These late derates are applied to launch path. Hence, data is coming slightly late. So because of this, now we are mimicking a hold scenario, pessimistic scenario. So thus now the simulations what we have performed by accounting the local variations through symmetric derating, we have improved the area and reduced the power dissipation. So thus this design became more robust. Okay, so that is how the FFG corner and SSG corner are benefiting compared to FF and SS corners. Yeah, in the earlier ring oscillator based cell delay extraction, we have figured out that the 3 sigma point is 382. 3 sigma point is 382. The mean is 460. 3 sigma away point from mean is 538. These are the values based on the earlier analysis. These are typical values, sample values. So now we need to figure out if this is the last value, performance corner, then what will be the FFG corner? What will be its value? So to figure out that, we need to get the samples of the same ring oscillator cell delay analysis. We need to perform on those situations where the delay is smaller and close to these points. Okay, definitely it will not cross 382, but it will be somewhere around these points. So in this specific scenario, I have represented a few of the values. These are typical values, and then when I have figured out, computed the mean, standard deviation, minimum, maximum, and based on these values, I made the Gaussian curve. Then for that, the mean is same here, and when the standard deviation, if you observe the 2, and the 3 sigma away point in the positive direction is 394, and the minimum one is 3 sigma below is 382. Okay, and that is this one. And this one is this point 382. 3 sigma minus 3 sigma is this one. So this one. So you will observe that this 382 point is coinciding with this one. However, note that 388, which is the mean value, is not same as then we need to figure out. Say this cannot be same as 460, definitely. But these values represent the local variation, and these are related to the local variation at FF corner. So now what we need to figure out is whether these values are the true values. To know that one, we need to understand the whether the samples what we have considered, are they realistic and do they represent the real data. Okay, the real data to a large extent we got it from the sample data from the last one, and from there do we get, if we extrapolate these values, do we get the realistic data. So to get to that one, we need to figure out whether these values, do they represent the right, do they give the right confidence. To do that one, we need to understand the standard deviation error. So that will standard deviation error for evaluating precision of sample mean. So as we earlier understood, the sample values what we have picked should represent the correct distribution. So to figure out that one, let us understand the standard deviation and what is standard deviation error. So as we know, mean is sample mean, which is sum by total number of points or sample points, and standard deviation is equal to the variability of the value from the mean, which is represented by root mean square. So this is the value, sample value, and how much it is away from the mean, and square of that. So it is to be done for all the values. This is usually we learned it from the statistics class. So now we will figure out how the standard deviation error will be calculated. Standard deviation error is calculated based on standard deviation divided by root of n. So if we take some sample points like this, just to give you some perspective, so we can easily calculate the mean, which is the sum of all values by total number of values. Here total number of values is 5. So now the mean is so and so. Now we will calculate the standard deviation. So since we know now the mean and the different values, so 5 minus 10.5 whole square, and the next value is 10 minus 10.5 whole square, like that all the values. So this is standard deviation is calculated. Now if the standard deviation error is calculated using this formula. So standard deviation is 5.35 and the number of points is 5, hence root 5, the value is standard deviation of error is 2.39. Compared to 5.35, 2.39 is quite high. Hence the sample points what has been picked up here is will not represent the distribution correctly. So that is how even in the earlier situation, when we are calculating the sample values or picking up the sample values, the FFG corner, though one precondition is that its last value should be 3 sigma value should be coinciding with the FF corner, but aside to that, the standard deviation error should also be less. So based on these points, we will get the FFG corner value. Similarly, SSG corner values also can be computed. In this sample points, the 3 sigma below deviation below point is 381. This one, as you know that our sample points based original sample points based with 3 sigma below point is 382. So here this is not coinciding, so one of the preconditions is incorrect, and aside to that we need to figure out what is the standard deviation error. Based on that also we can say whether these points, this distribution is correct, and hence the FFG value what has been mentioned here, which is this one, is it correct. These are some more sample values which will have the 3 sigma deviation below point is 376. That means like it has crossed the 382 picosecond which we have computed earlier. So definitely this will not be the realistic scenario of the distribution, and this FFG value will not truly represent the actual samples which we have to use. In the sense like there is something called population data, sample data. This one you will observe even during the election voting. Sometimes these election pundits, they will say that based on our sample survey, the so and so party will come, their seats will be so and so and all. But in the actual reality, you will observe that the numbers will be different. The reason being their sample data and the population data, which is the actual data which will be seen during the election time, will be entirely not coinciding, because their standard deviation of error is larger when compared to the standard deviation. Hence their estimation is going wrong, even though they may say plus or minus 4% and all, actually it is not representing the true samples. So in this case also, this is not representing the true FFG mean. In the original samples, you have observed that the mean is 460. That will be that we called as TT. And if you observe the when we have taken the samples near these points, such as this one, then you will observe that the TTG here it is 464, which is different to this one. I just wanted to mention that here these values, they will not coincide. That means like TT and TTJ and TTG global corner, that means which represent the local variation of this distribution at the TT corner, they will not be coinciding. They need not be. Okay, definitely not. So that point I just wanted to mention here. Here we will understand the process corners of a nominal condition. Why I mention nominal conditions mean like this distribution will depend upon the voltage and temperature situation. So here this data is representing the typical. This is the slowest value, this one, okay, and this one is the fastest value. So now if you, this is the slowest, okay, so now if you observe, so this is the cell delay in the x-axis and this is the probability distribution. So typical one is having the largest probability distribution. And if you observe, so here the cell delay slow and fast are slightly interchanged. You can think that this is the large one, then plus, and this is minus side of the typical. Okay, so here if you observe, there is this is the SSG corner and this is the FFG corner. Okay, so this will represent the local variation of the fast case. This will represent the local variation of the slow case. And here you will observe that the slow SSG probability distribution is having a larger peak than this one. But that does not alter the outcome, because when you figure out these distributions, when you have accumulated different sample points to get this distribution, you have actually considered many points, and out of that, here in this situation there were not so many points. And here if you consider the local variation, here you are considering the more points, and here these points are the maximum probability distribution. So the distribution wise, the value at the local variation, because we're collecting more points, it will appear like more, but that does not alter the outcome. Outcome is delay only. So this SSG corner delay will be smaller than this slowest corner. Larger, I mean, sorry. So this SSG mean is okay, sorry, smaller than the slowest value. So actually here the items are interchanged. So that one, and the setup corners in general should be be checked in the slowest corner, and the hold corners must be checked in all corners here. And if you see the nominal conditions here, so here this distribution represented by the blue histograms, and these green histograms are represented by another curve here going this one. These two are different scenarios. If you observe this SS 1.0 and SS 0.65, That means like we are analyzing two different conditions. So in this one, that green one is 1.0 curve here represented. Same thing for SS corner at 0.65 is represented by blue curve here. So based on the voltage, similarly if you apply the temperature also, then these distributions are changing. Assume you are using the same process monitor, ring oscillator, same inverter and all, their distributions are changing because the delay sampled values will be different. So you can figure out that the SSG value at 3 sigma at 1.0, SSG value at 3 sigma at 0.65 are different too. And you will also observe that the SSG plus 3 sigma at 0.65 is far larger than SSG at 1.0 at plus 3 sigma. That is why the variations are more at the low voltage. Hence, we need to arrive at more PVT corners as per the different VT or other conditions. These are different references which I have referred to in making the slides. Feel free to go through them. Process corners and variation model for timing will be discussed briefly here. So to connect how the process corners and the variation model are related. Okay. So as we have observed, SS corner, FF corner and TT corner, I am not mentioning specifically. So these corners are used along with the OCV variation model to improve the accuracy and correlation of simulation to silicon data. And when SSG, FFG and for completeness mentioning TTG are used to use along with the AOCV variation model or Liberty variation model. So these AOCV and LVF are advanced models compared to OCV, and in terms of accuracy, you will observe that this LVF for different path numbers, this is the delay, this is the delay of different paths, and you will observe that it is very closely converging with respect to the Monte Carlo simulation, which is very good. So that means there is less pessimism in LVF. And coming to the next yellow line, this is AOCV. That means like here there is somewhat more pessimism than the LVF in terms of accuracy. Hence, this is slightly far away from the Monte Carlo simulations. And coming to the OCV, this is represented by the blue line, which is far away from the Monte Carlo simulations. Hence, it will lead to more area and power dissipation. So this is how the process corners and the variation models are connected. Thank you.